everybody. Today we're going to start Unit 4, talking about mechanical energy and work. So first thing we'll define is mechanical energy. So energy is going to be represented by the capital letter E for energy. And this is mechanical energy specifically. Is defined as the ability to do work, which we'll define later, or change the motion of something. So something has energy if it can cause a change in motion of something else. Energy is a scalar quantity, so it has no direction. We'll talk later that it can be positive or negative though. So you can think about it as increasing the energy or reducing the energy of something. The unit is a joule, which is a capital J. So first definition here is kinetic energy, which is represented with a capital K, has the same unit. All these energies have the unit joule. And the kinetic energy is the energy of an object in motion. So if we have some object that has some mass moving at some speed, it's going to have kinetic energy. It could hit something else and cause something else to move, which kind of fits in with this previous definition. And our equation for kinetic energy is going to be 1/2 times the mass times the speed squared. And then if we have multiple objects and we wanted to know the total kinetic energy, so for a system of objects, we'll just to find the total kinetic energy, we just add the kinetic energies together. All right. Next definition, the other type of energy that we'll talk about today is potential energy. That has a capital U. This is the energy through position and arrangement in some sort of between two objects. So only a system of objects can have potential energy. An object by itself can only have kinetic energy. So an object can only have kinetic energy. But if we consider the object and something else, then it can have potential energy. So I think the easiest one to think about is gravitational potential energy. So this is an equation to jot down. Potential energy equals mass times our gravitational field strength, G, times h, which is going to be height above some reference point. So if this is the surface of a planet and we have something that is 2 meters up, it has potential energy relative to the ground. And that's because we're including the object here and the planet, so in this case Earth, in our system. So because the rock is held above the ground in Earth, or relative to Earth, it can have gravitational potential energy. The other type of potential energy is elastic potential energy. So this is relative to a spring. So if we have a spring and we compressed it some distance x, it has potential energy. If I was to put, a ball right here, it could cause an increase in kinetic energy of this ball. So x is going to be the compression or the stretch. Remember, K is that spring constant. So yeah, two different types of potential energy. Let's do some examples. So we have a 2-kilogram bird flying at 5 meters per second, 10 meters above the ground. So what is the mechanical energy of the bird? Okay, so a bird can only have kinetic energy. So if we think about the bird itself, not relative to where it is, it just has kinetic energy. So 1/2 mass times the speed squared. which comes out to 25 joules of energy. But if we think about the bird-Earth system, so now we get to include the Earth, which means we get to include this 10 meters above the ground. The bird has energy that is comprised of kinetic energy and potential energy. So we're just going to add them together for the total mechanical energy. So that's going to be our 25 joules plus the mass times g times the height, which comes out to a total of 221 joules of energy. All right, next one. We have a 7 kilogram block on a 1.4 meter tall table. And it is, oh, I drew this kind of wrong here. Cool. So here we are, we've got a spring that's being compressed 0.1 meters. We have a block that's 7 kilograms. And we have a table that's 1.4 meters tall. So what is the mechanical energy of the block, spring, earth system? So we've got the block here. It is at rest. Okay. So if I think about all my types of energies, I've got kinetic energy, I've got potential energy from the earth and the spring. We're at rest, so there's no kinetic energy. But I do have some potential energy because we are above the ground. So the mass of the block is 7 kilograms times 9.8 times 1.4 meters. And then we also have been compressing the spring. So that's our 1/2 times our K, which is 500 Newton meters, and then 0.1 squared. So our total energy is about 99 joules. Right, a couple more definitions. So the next one is work. So I mentioned work earlier. Work is defined as a change in energy. So there's a couple of different ways to think about it, a couple of different equations. The unit is still a joule because we're just talking about energy. So one equation, one way that we can calculate work is by, if we have something pushing an object, so a force, and moving an object some distance, we can figure out for the work by taking the force and multiplying by the distance that something travels. And it's only going to be, so let's say I've got a block here and I'm pulling it to the right with some force over some distance here. The further I pull this object, the more energy it's going to require from me. So that distance is what we multiply by, but we only multiply by the parallel component here of the force. So if this is at an angle, it's going to be the cosine component. So you can either say F parallel times the distance, or our equation is going to be F d cosine theta to figure out the work done by a force. This can be negative. So if I had let's say I had some friction pulling in the other direction, but we're moving to the right, this force would cause a negative work. So work can be negative. If you have a graph of force versus distance, let's say we had a steady force going over a distance here, The area would be force times distance, or the area here is my work. Okay. All right, and then last definition is the work energy theorem. So the work energy theorem states that the net work, which is the work done by all the forces on an object, equals our change in energy. So if I had multiple forces acting on the same block, some are positive, some are negative, we would add those works together. That'll equal the change in energy. And if we're just looking at an object, we're not looking at a system of objects. So for an object, my net work is equal to my change in kinetic energy. And that's because objects can only have kinetic energy if we don't include them in a system. So let's look at application of this. So we have a 40 Newton box lifted at a constant speed, a height of 2 meters. So let's look at the free body diagram. So we have a 40 Newton box here, which means that's the weight is 40 Newtons. And I'm lifted at a constant speed. So that means that I have balanced forces. So there's 40 Newtons pulling upward as well. And we travel 2 meters. So remember, work is going to be force times distance. And then for these, we're in the same direction as the motion. So we can include the cosine theta here, but I'll show you how it kind of cancels out. So pulling upward, that tension force, 40 Newtons, traveling 2 meters. And there's the angle between this path we're traveling and the force is 0, and the cosine of 0 is just 1. So we didn't really need to include that because we were already parallel. So that's a total of 80 joules. The work done by gravity, again, we have 40 Newtons. Okay. We're traveling 2 meters, but it's in the opposite direction. So it's pulling opposite of the motion of travel, or that angle between the path we're traveling and the force of gravity is 180 degrees. The cosine of 180 is -1, which means that gravity did a -80 joules. Another way to think about it is if we were somewhere where there was no gravitational field and we pulled with 40 Newtons, this would accelerate the box. It would increase the energy, but we're essentially decreasing the energy by pulling backwards with the weight of the box. So the net work, we just add our works together. So 80 plus -80 equals 0 joules. So we're just looking at the object. We're not including the Earth in our system. So this box, which can only have kinetic energy, did not change its speed. It did not increase its kinetic energy, so there was 0 joules of work done. All right, last example. A box is pulled across a rough surface, a distance of 4 meters, with a 20 Newton force angled at 30 degrees. And there's a 5 Newton friction force. So I've got 5 Newtons of frictional force, 20 Newtons at a 30-degree angle. And I do have some gravity and some normal force here, but you'll see they don't really matter for us in this problem because we are traveling to the right a distance of 4 meters. So the normal force and the gravity force, we get to kind of ignore for this question here because they are perpendicular to the path that we're traveling. So we're moving this box to the right. Okay. So we're not changing our distance up or down. So force times distance is just going to be something times 0. So work done by the normal force and work done by gravity are both going to be 0 joules. And that's because we're not moving up or down, so those forces are doing no work. What is the work done by tension? So work is going to be F times distance times cosine theta, because we are at an angle here. So 20 newtons times 4 meters times cosine 30 is going to be about 69 joules. What is the work done by friction? Remember, so we're in the opposite direction, so it'll be force is 5 newtons times 4 meters, but we'll multiply by -1 here, just make the answer negative, so -20 joules. And the net work is going to be that work done by tension plus the work done by friction for a total of 49 joules. We're just looking at an object again. We are just changing the kinetic energy. So we should be able to use this net work and set it equal to our change in kinetic energy. It's going to be our final minus our initial. We know we start from rest here, so we don't have any initial kinetic energy. I know my net work is 49 joules. And that's going to equal 1/2 times the mass, which I did not give you. Let's make it up. It is a 2 kilogram box. And we want to figure out how fast it's going, so that'll be our final velocity squared. So 49 equals 1/2 of 2 is 1, so that's our final velocity squared.